What causes earthquake swarms at Yellowstone Supervolcano? We sometimes see small or even bigger quakes, and a lot of people ask, what's happening? Is Yellowstone going to erupt? Well, it will erupt at one point, but it may be hundreds of thousands of years from now. And the most likely scenario, from what the Yellowstone Volcano Observatory geologists tell us, that it could be a hydrothermal type of an eruption from a geyser. We know that Yellowstone has over 60% of the world's geysers and over 10,000 hydrothermal areas. Now, what causes these earthquake swarms? And they're a natural part of what's going on in Yellowstone. According to USGS, the recent Caldera Chronicle, earthquake swarms are common at Yellowstone, but why do they occur? Are they driven by magma migration or water, steady creep along faults? All three are possible, and tracking the style of earthquakes can reveal the causes. Earthquake swarms, sequences of elevated earthquake activity with no clear main shock, are common at Yellowstone and many other places. Swarms occur in a variety of volcanic and tectonic settings. Kindly support my Patreon account since YouTube has again demonetized my YouTube channel. The daily posts are 5 videos daily, and they are totally different from what I have on my YouTube channel. Thank you so much for your support and that you find all my content so interesting. You'll find the Patreon account details in the description box below. They occur in a variety of volcanic and tectonic settings and have several possible causes. Some swarms are driven by slow fault slip that causes earthquakes on few sticky patches of the fault. Other swarms are generated when magma-filled cracks push their way through the crust. And perhaps most commonly, swarms are generated when aqueous fluids, that is the water, enters and interact with pre-existing faults in the crust. Sometimes combinations of these mechanisms might be active in a given swarm. But how can we distinguish among these processes? Such a determination is not simple and remains an important topic of ongoing research, but we can examine several aspects of swarms to guide our interpretations. At the Yellowstone volcano, everyone wants to know, is the swarm driven by magma? The question is particularly pressing if the swarm is occurring at shallow depths within a couple of miles of the surface, because a shallow, magmatically driven swarm could potentially be a precursor, of course, to an eruption. A primary distinction between magma and water is a driving mechanism is the width of the crack required for the fluid to move through the crust. While water can travel through very small pre-existing cracks or faults within the crust, magma requires a much thicker crack to allow the magma to continue to propagate without quickly cooling and solidifying. We can potentially observe several properties of the seismicity related to this difference in crack widths. For example, earthquakes triggered by water will occasionally occur as fault slip on the cracks and faults along which the fluids are propagating. That is, the two sides of the crack hosting the fluids are still in contact with each other, but the fluid reduces the clamping forces and lubricates the fault enough to allow it to slip. In contrast, the walls of crack hosting magma are generally not in direct contact with each other. They're separated by the magma itself. So rather than occurring by slip between the walls of the crack, earthquakes will instead occur near the crack tip, the point ahead of the magma where the crack is starting to open, or off to the sides of the crack because the opening of the crack stresses the surrounding rocks. In the case where a swarm is caused by slow fault slip, earthquakes repeatedly occur on the same small sticky patches within a dominantly creeping fault. There may be no progression of seismicity at all, just the same small patches constantly generating earthquakes. In addition to seismic observations and the pattern of earthquake locations, We can also use deformation measurements to examine changes in the shape of the surface above the earthquake swarm. Opening of thick cracks required for magma propagation creates a warping of the Earth's surface, which becomes increasingly large and easy to observe for the shallow cracks that would be of most concern. Swarms driven by aqueous fluids, the water that is, pressurizing pre-existing cracks, in contrast, would cause only very small surface warping, mostly due to slip in the cracks themselves, and is usually too small to be observed. Slow fault slip, if large and shallow enough, can be observed on the surface, but the pattern of deformation is very distinct from that caused by a magma-filled crack and therefore easy to distinguish. When interpreting the processes that might be causing an earthquake swarm, it's also important to consider the context. At Yellowstone, for example, the last magmatic eruption was a lava flow, and that occurred about 70,000 years ago. And we had another 80 eruptions since then. But the area is home to one of the most vigorous hydrothermal systems on the Earth, so even though eruptions are rare, we observe many small earthquake swarms at Yellowstone every year, and relatively large earthquake swarms every few years. The characteristics of the swarms and their context indicate that the vast majority are driven by water moving through the subsurface. So it's mostly the water that causes these swarms. As an example of putting this all together, let's consider the June to September 2017 Maple Creek swarm, the second largest earthquake swarm ever recorded in Yellowstone. About 2,400 earthquakes, the largest of which was 4.4 magnitude, were located over about 3 months in the northwest part of Yellowstone National Park between North Geyser Basin and Hebgen Lake. The earthquakes moved around over time but were occurring in an area that hosts numerous existing faults. The migration of the seismicity was rapid and no ground deformation occurred. Observations like these suggest that water was the cause of the swarm. Water was also the most likely cause of an intense swarm that occurred near Madison Junction in the western part of Yellowstone Park in 2010. A more complex case was the 2008-2009 Yellowstone Lake swarm. Rapid migration of earthquakes in this swarm suggests it might have been driven by a low viscosity fluid such as water or even carbon dioxide, which could move easily through small cracks in the subsurface. But unlike other recent swarms in the park, this swarm was accompanied by small amount of observed surface deformation, making it difficult to completely rule out a magmatic source. That was for the Yellowstone Lake swarm. Fortunately, with improvements in the Yellowstone monitoring network since 2009, we could learn even more from similar swarms that might occur in the future. Each Yellowstone earthquake swarm is unique, lasting minutes to weeks, and including a few to 1,000 of earthquakes that might or might not move around over time. With long-term investments in seismic and deformation monitoring, we continue to learn more about the Yellowstone system by studying this common form of seismicity. And of course, even today, let's see what took place. We'd had a couple of, on the northeast part of Wyoming, we had, I would call it a swarm as well. Let's take a look at the map. Okay, so here we are at Seismo Berkeley. I'll leave a link. And this is what we have here, Yellowstone. Now, we saw from the map I had before, this is the magma area around the west and Yellowstone. It's the shape of a Y. The western part goes under the San Andreas Fault in the Walker Lane Fault System that has all the high threat volcanoes of California and the west. And the other arm, the eastern arm, goes through Salt Lake City, through Nevada, Salt Lake City, into Wyoming, then makes a 90-degree turn into Idaho. That has, of course, the Idaho volcanic field. So let's see, these are all, of course, small earthquakes, but I would call them a swarm, especially the ones up there You can see them right there. There they are. Between Hebgen Lake and this area here. These blue are all today, and about a 10 to 14 kilometer depth. There's more down there. Okay. These are small, as you can see. Okay, and this is Yellowstone Lake right here. Another 3 earthquakes there. This one was shallow. And this one is pretty shallow as well. And this, of course, deeper. But this is the caldera is around here. Yellowstone Lake is on the southeast part of the caldera, which is only about 3 miles down from the surface. I'll leave links below for you for this. This is from Caldera Chronicles Yellowstone Volcano Observatory. Thank you for your support. Please leave your comments. Thank you.